Welcome to Study Loop.
So we have the quantum harmonic oscillator, and we're modifying the potential so that it looks like, the familiar part plus an extra part due to the presence of an electric field. So we have like minus E, let's see what units do they use, QE times X. And this problem particularly writes this as K, 1/2 KX squared minus QEX. That's the same thing as what I was writing with omega being the square root of K over M. So the Schrodinger equation for this is going to be, negative H squared over 2M times the second derivative with respect to position. We're just writing down the one-dimensional case. So that's our kinetic term plus our potential term, which is 1/2 M omega squared X squared minus Q EX. All of this is the operator acting on the wave function psi, and this is equal to our energy eigenvalue times psi. All right, so that is part A. Now what we want to do is use a change of variable so that this looks like the ordinary quantum harmonic oscillator. And so to do this, just note that if we use the variable, they call it like x tilde, as x minus QE over the M omega squared, then substituting this back in, and we can kind of complete the square a little bit, what we get is the Hamiltonian in terms of this new coordinate is, the position or the ordinary kinetic term plus 1/2 M omega squared X tilde squared minus a constant term, which is Q squared E squared over 2M omega squared. So this last constant term is what they're calling V naught, in the example listed in the book or in the problem description. And so next up, we have to write down the energy eigenvalues, which is actually pretty easy because this part is our ordinary quantum harmonic oscillator term. So the energy eigenvalues are going to be the same with an additive constant. So it'll be h bar omega times n plus a half plus this extra potential term, which really is actually negative. So minus q squared e squared over 2m omega squared. So those are our eigenvalues. And then our eigenfunctions, we can just take the ordinary Hermite polynomials that are the typical solution to this and replace x with x tilde. And so they get kind of nasty. There are lots of algebraic factors to consider, but I'm going to write all of them down. So this is our normalization factor. Let's see, and this is pi times h bar. This is all to the fourth power. And then we have e to the minus m omega x minus QE over, let's see, what is it, m omega squared. This is squared, and then this is divided by 2h bar. And then this is multiplied by the nth Hermite polynomial, which is evaluated at the argument x minus q e over m omega squared. So this is like the nth wave function. So these are your new wave functions in this particular field in terms of the original coordinate x. And so, if you want to write it in terms of the x tilde, which I should have actually written this as an x. This is in terms of x. If you want to write it in terms of x tilde, you'd basically just take the substitution that we wrote down earlier, which was just x tilde equals x minus q e over m omega squared. So everywhere you see that, you just put an x tilde, so up in this exponential and also in this Hermite polynomial. But that's really all there is to this problem. It's actually, with that trick, it's a very simple solution if you can, kind of realize how that completing the square works.